Peter Sierck is an industrial hygienist and biobiologist who's been conducting electromagnetic field surveys and applying field reduction methods in homes, schools, and workplaces for over 30 years.
Good afternoon, ladies and gentlemen. It's a pleasure being here. Recently, I received a call from a client who was concerned about the new installation of a 5G antenna in their neighborhood and the consequences RF exposure. We went to the residence and conducted an RF survey with a spectrum analyzer. And guess what the results were? The highest exposure was from a Wi-Fi router next to the home office work desk. And secondly, a cordless phone on the nightstand in the bedroom. As a medical professional, you like to obtain a detailed diagnosis before you design your treatment plan. The same is true with a building. What I would like to do here today is give you the tools so that you can diagnose and treat, i.e. mitigate, buildings to create a low EMF environment for yourself and for your clients. Sometimes it's a balancing act between what we want, what we need, what we can change, and what we may have to let go of. And when we talk about electromagnetic fields, we talk about waveforms. So the wave and the waveform are very important in EMF, or electromagnetic field and radio frequencies. So let's have a look at a wavelengths. So we have a sinusoidal wave right here from zero going up, down, below, and back to the zero line. That is one wavelength. And if this wavelength occurs within 1 second, then we call it a hertz, 1 hertz. If two of these waveforms occur within 1 second, we call it 2 hertz. And if you look below, if we have 12 of these cycles per second, then we call that 12 hertz. This is an important terminology we will need to use later on when we talk about instrumentation. So you will hear the terms hertz, kilohertz, megahertz, gigahertz. What does it mean? Well, 1,000 hertz equal 1 kilohertz, and 1,000 kilohertz, 1 megahertz, and 1,000 megahertz, 1 gigahertz. The frequency spectrum in which wireless devices, which we currently have, operate in ranges between about 100 megahertz and about 3,000 megahertz. So that's the arena we are talking about when we talk about radio frequencies. So important are the frequency, the wavelengths, and the energy which are in it. So the longer a wave is, that means less frequency, the more penetration these waves have going through concrete and walls and glass and so on. And the shorter the waves are, the less penetration they have, which is actually an issue with the 5G generation of the higher frequency, the millimeter waves, because they're not penetrating very well. The tree in between will block the signal, and therefore more and more antennas need to be installed. That's one of the reasons why we see so many coming to your hometown. Okay, so let's do a physical for your building. So what do? We do an intake first, right? So we do a walkthrough around the building and look for obvious sources, such as power lines, substations, transformers, and so on. And then we focus on the inside on the building. What are the obvious sources? So maybe you can see the cordless phone and other things you may not detect very easily with the naked eye, and you may need to have some testing tools, some meters, and we'll talk about what meters would be appropriate to it. We definitely want to identify where the circuit breaker panels are, because that's where the electricity is coming into the building. We want to measure, we want to analyze the data we have, and based on what we find in the building, we develop a treatment plan or a mitigation plan for that particular building, right? So we have naturally occurring fields on this planet as well as in the cosmos. But these fields are basically DC current, direct current fields, or static fields. And what we are talking about are man-made fields, which are not naturally occurring on this planet or in this universe. So let's look at the ones we are really focusing on. So AC stands for alternating current. That's the type of electricity we have in our electrical wires. So we have magnetic fields, electric fields, magnetic fields, radio frequencies, and dirty electricity. Those are the main sources of EMF in a building. One could include nowadays also lighting, because we are going away from the incandescent light bulb and we're going over to compact fluorescence and LED, which can be also a stressor, and issues are associated with them, and we will see more of that in the near future. So when we talk about the AC, the power distribution, I basically differentiate between the wired way of supplying energy and the wireless way. So it's all about energy transfer. So we're transferring energy from a power station over the grid back into our building at the electrical panel, and then it goes into the wires inside the wiring and then to the individual power cords. And the AC system has a magnetic field and an electric field. So let's look at the magnetic field first. The magnetic field is created by a current flow. You actually have a hot, which flows electricity in this direction, and a neutral going in the opposite direction. And they actually cancel each other out in a well-maintained installed building. So therefore, we shouldn't have high magnetic fields in a residential building. But the magnetic field strength is dependent on the current flow. Let's use an analogy. Think about plumbing. You have plumbing pipes and you have a faucet. And once you open up the faucet, the water starts running. That's the analogy to the current flow. Once I close the faucet, then no current flow, no magnetic field. So magnetic fields dependent on current flow and not voltage present in the system. In the US electrical system, we use about 60 hertz frequency in our power grid. And magnetic fields are measured in milligauss, or mg. Now let's talk some of the sources in buildings. First of all, on power lines. Why do they create high magnetic fields? Because that cancellation effect is eliminated as we are separating the conductors apart, and therefore we get relatively high magnetic fields with power lines. Another source is substations, because same scenario, we're separating the conductors from each other. And then eventually we end up at the circuit breaker panels. And you can see that there are a lot of wires running into the panel. You got the main line coming in on the bottom here, and then you got the circuit breaker, and then it distributes into the different circuits. So a lot of current flow here. So therefore, there are high magnetic fields associated with circuit breaker panel. Now, here is a scenario where we really, this makes the point why we all should have EMF meters in our pockets when we go and rent an apartment or a condo or purchase a building. In this particular scenario, this is a huge apartment complex which has been built. And by chance, I had an opportunity to walk through there. And this is a building design where the entire electrical wiring for this entire building complex runs through one of the residential units. It will be covered with drywall. Nobody will see it, hear it, smell it, taste it, but it will be there. There will be a dramatic magnetic field here. Now let's assume this would be the headboard of the master bedroom, or the wall where the crib for the baby is standing. So really a situation which is irresponsible in my book from the builder to build it this way. Why did they do that? To save money. So, and that carries on through the public spaces, and that means hallways and other parts of the building where they run the wires in such a fashion, which is very unusual. So that's where our meter helps to determine where the sources are. We have an older building, we can have knob and tube wiring where the wires are again separated, creating large magnetic fields. Another source is what we call point sources. Anytime you create coils with electrical wires with current flow in it, we call that a point source. Point sources, for example, are motors, which are in refrigerators and other devices. So this is a wonderful great air purifier in a bedroom. But if we look at the meter, we have a Gauss meter here, which measures the magnetic fields. We have 1500 milligauss here. That is about 1,000-fold higher than what we should see, but it's related to the electric motor here. Once I turn that electric motor off, 0, right? So we have something which we call a golden arm rule. About 3 feet distance. Oh, can't reach my arm out here all the way. And that's normally the distance at which the magnetic fields from a point source dissipate to the background levels, right? Give you another example. This is a remodel. The kid's bedroom is supposed to be placed right here. And the room is being remodeled. The contractor, as he removes some drywall, noticed that there's an electric panel right here and the main power is coming here. And this is supposed to be the headboard wall. So upon coming out there and doing some measurements, we recommended to the client not to use that as a headboard wall and use the opposite wall. However, the client's, try your best and try to eliminate the fields. So we have magnetic fields due to the current flow, but we have also electric fields due to all the wiring. So what we did is we used some copper wire mesh and covered this entire area to eliminate the electric fields. And then we used some special alloy material to put it over the circuit breaker panel and the main incoming lines to shield off the magnetic field. Result, very insufficient. We got about a 50% reduction. And these kind of shielding materials are not inexpensive. So source removal or relocation in this particular scenario is a much better answer. Eventually, the client was convinced that to put the bed on the other side of the room. So sometimes you can, and sometimes you cannot really do very much about the situation in the building. Now let's talk a little bit about background levels. What's kind of like normal in a residential building? It should be 0 or 0.1 up to 0.5 is something which is normal, which we see in buildings without high tension power lines, so substations or transformers on the outside. They did a study in the US of 1,000 randomly selected homes, and it showed up with 0.9 milligauss. And some of the guidelines you can see suggesting magnetic field levels below 1 or 2 milligauss. There was a meta-study showed that a higher incidence of childhood leukemia and cancer can be attributed, or a higher incidence, odd number is at 3 and 4 milligauss and higher. Even though the World Health Organization declares EMF as a possible carcinogen, they still say up to 1,000 milligauss is okay. Well, this is a totally unrealistic number. You will never find 1,000 milligauss under a high tension power line or anywhere else. You really have to put your butt on top of a transformer to achieve that. So we want to be somewhere below 1. Right? If you start reading research paper, you will find different units. For example, in research papers and internationally, the unit of microtesla is used, and in the United States, we use the term milligauss. So here's a little comparison. So 1 milligauss would be about 0.1 microtesla. Sometimes nanoteslas are used. So let's make ourselves familiar with that. To deal with some of the conversions, there's actually a wonderful conversion application out there. Just recently came out, either for iPhone or for Android phone. So go download it. It's called the EMF calculators. There are a whole bunch of them when you go in the App Store. Look for the one which has this W here. It's from a company called Wave Control, and it's a wonderful conversion tool, very easy, very user-friendly. So we already talked about the most common sources of magnetic fields, but here are some other ones we need to pay attention to, and that is wiring errors in buildings. If a building is not wired correctly, then we can have large magnetic fields. We can also have current flow on utility pipes, like gas pipes and water pipes, which then can also create magnetic fields. And anytime you have a lot of transformers, low lighting systems, transforming from 120 volts to 12 volts, therefore we have a lot of transformers. So we need to look at that as well. So for example, we see here with a Gauss meter, I hold it against the wall and the light switch and have about 132 milligauss. That shows me that's not quite right. If it's maybe 1 or 2, yeah, but it's an indication that there is a wiring error occurring in this building. So what do we do then? Well, we need to get an electrician out there to actually look at the wiring. The most common mistake is what we call ganging of neutrals. What you see here is a wire nut, and you see wires coming from this circuit going in this wire nut, but also wires coming from this circuit going into this wire nut. That is not appropriate. So a lot of detailed work needs to be done sometimes to actually find the flaw in the electrical system. Here's a diagram of what we just saw. So here's the electricity coming from the panel going to your light bulb. And here's another coming from the panel going to some other electrical appliance. And the neutrals are put together. That should not be the case. There should be 2 nuts, one connecting these 2 wires and one connecting these 2 wires. And then the magnetic field problem will dissolve itself. So with other words, wiring issues in buildings we can address relatively easily. That is not an issue. We just need what? An electrician to do that. The other source of miswiring which occurs frequently in building is sub-panels. And on a sub-panel, what we see here is a ground wire going to the neutral bus. That is correct on the main panel. But if we're going to a sub-panel, that connection should not be here. What we want to see is a situation like this, where we have an extra ground bus where the ground wire actually goes through ground bus and has no connection to the neutral bus. So who fixes these issues? Well, electricians do, right? Okay. What are the indicators when you have a tool, a measurement tool, to find out? Well, if you have large fluctuations, here you can see that we're actually measuring. It started out at 19 and it went slowly down. These are measurements in one location. I'm not moving around. So it should be fairly equal, the measurement data. Now I have 4 pictures of the same location at different times. And you can see it varied from 1 to 3 to 14 to 20 milligauss in one location. That's an indication that there is some major miswiring going on or stray currents on pipes. And we need to find out where it is and then fix it. So in summary, wiring errors are the largest source of elevated magnetic fields in residential buildings if we're not close to power line. How do we fix it? We need to track down what circuits there are. There are easy methodologies to do that by flipping circuit breakers on and off and monitoring your measurement device. So usually biologists are very skilled in doing that. And you need an electrical contractor who can actually go in and fix the situation. Here in Southern California, we have our major wiring expert, which is Orr Miller. He loves to put his hands into electrical wiring situation and trace it down until he finds the last little bit of failure in installation. So we need somebody who can work with you. It doesn't have to be necessarily a trained electrician. We can teach them as we go along. All right, so straight currents, just one more time, are current flow on water pipes, on gas pipes, and drainage pipes, and where current is flowing from one building to the other. You may not be the cause, your neighbor may be the cause. So how do I find that out? Put your Gauss meter right on the plumbing pipe. And if you see an elevated level, then there's a current flowing on that pipe. How do we fix that? Well, we need to disrupt the continuity of that conductive material. So we call that a dielectric union. Basically what it is a piece of plastic which gets inserted into a metal pipe. And since plastic is not electrically conductive, the current flow will be stopped. And when there's no current flow, there's no magnetic field, right? What kind of meter can we use? There are many, many different meters out there on the market. We will actually have tomorrow a workshop on how to work with meters and the do's and don'ts and how I can trace things down. I will show you a whole plethora of different consumer type instruments. This is one which I like a lot because it has a very broad display here, and you can switch between the magnetic fields and you can switch between electric fields, and it even has a setting for radio frequencies. So that's kind of like my favorite consumer instrument. Now, where do we get some of the recommendations from? I personally go by the European PAM recommendation as a document which was issued in 2016, EMF Guidelines for Prevention, Diagnosis, and Treatment of EMF-related health problems. So it's not only about the treatment, it's also about the diagnosis of patients. What they have a very unique approach, which I like a lot, and that is that we have 3 different categories. We have a daytime exposure category, we have a nighttime exposure category, and we have a category for sensitive populations. For example, electromagnetically sensitive individuals may not be able to tolerate what a normal person can tolerate. So you can see that is the setup basically on the European guidelines, and we will see that one more time when we get to other fields. Okay, we talked about the magnetic fields. Now we're getting to electric fields. Electric fields are influenced by our body. Electric fields have the propensity to go to ground as fast as possible. So since our body has a lot of liquid, which is conductive, and we have less resistance than the air, so the electric fields love to go through our body. That is a problem when we actually measure fields, because if we hold the instrument in our hands, the field will be attracted to the body and not to the instrument, and therefore we get a false reading. So we actually need to put the instrument further away, step back about 6 feet, and then get the measurement result. The electric fields, contrary to the magnetic fields, are actually created by the voltage being present. What's that? Let's get back to the analogy of the water pipe. So we have the water pipe with the spigot, and when we turn it on, then the water flows and we get the magnetic field. But if we turn it off, there's no flow. But what we still have is water pressure. And that pressure is the same thing as the voltage in an electrical system. Actually, in the early days of Edison and Tesla, they actually called it electrical pressure. And so as long as something is energized, there's there's voltage present. We have an electric field extending out from the wiring around it. So when we do measure, again, we want to make sure that we are not interfering with the measurement result. So we hold it away, or we have it on a pole, which is a non-conductive pole. All right. So you see this meter also has a selection of electric fields. However, it only has 1 sensor in here and not 3. So basically the point is electric field measurements are complex, and we really have to have a good understanding to get correct readings. Okay. Now, how do we eliminate the electric fields? Well, believe it or not, we all in our residential buildings have electric fields coming out of our walls because of the wiring we have inside our walls. Because we use a wiring system which is called a Romex cable, which is not shielded. And therefore, the electric field is being emitted out of the wall into the adjacent room. And the closer you are to the wall, the higher is your exposure to the electric fields. How can you fix that? Well, in new construction, very easily, we take some metal sheeted wiring, and this metal is then connected to ground. And so as the field emits from the wire, it hits the metal and then gets directed towards ground, and it never comes out of the wall, and therefore we don't have electric fields associated with that environment. Well, that's good for new construction. But what do we do if we have an existing building and we know we have high electric fields in our bedroom? We spend most of our attention onto the bedrooms, because that should be a safe place, a EMF sanctuary, because we are regenerating, we are recuperating, we're doing cell repair at nighttime. Okay, so another option is what we call a cutoff switch. So what we do is we go and identify the circuits by actually flipping off the circuit breakers to find out until the field is collapsed, and then we know which circuits are involved in creating this field in this bedroom. And then we have an electrician install a box similar to this, and we have a little remote control. When we go to bed, we can flip the switch and the circuits are turned off and no electric field. However, don't do that without measurements before and measurements afterwards, because I have seen that one just looks at the circuit breaker panel and it says master bedroom lights, and that must be the circuit and the only circuit. That may not be the truth. So sometimes by flipping off one circuit, the other becomes stronger because there's now not a cancellation effect anymore. So that requires a little bit of testing, right? So what other options do we have? Well, the same principle applies too. We could actually use the shielding material, and rather than wrapping it around the wire, we can put it onto the walls where the electric field is coming out of. And that can be achieved by using paints, by wire meshes, by foils. We attach them to surfaces. So let's look at a real life scenario where we actually do that in somebody's home. So we have a master bedroom here, we have a headboard wall, and here are the results of electric field measurements. We call it the 9-point measurements, where we actually measure 9 points on the bed itself. And you can see at the headboard wall, we have 7, 10, and 7 volt per meter. And down on the bottom, we got not less than 1, and somewhere in the middle, we got about 1 or 2 volts per meter. So we want to eliminate that. So let's apply what we just learned. That is, we can shield a wall. So we apply some shielding paint onto the headboard wall, and then we go back and remeasure. Why didn't we paint the wall all the way to the top? Why? Because the wiring is down here between this outlet and that outlet here and that outlet over here, and there's no wiring up here. So that's why I stopped painting it here. Now, the measurement results, you can see the fields are low, below 1 volt per meter, but you can still see that there's some influence from this side wall. Well, since I want to go all the way out and see what I can achieve, I will paint also that side wall, and then we need to connect a grounding straps and ground wire to actually ground the system out. That is essential for any type of shielding work. So now let's look at the final results. See, I put some primer on top of it so that the black paint is covered. And now let's look at the results. We have 0 back here, and the highest reading right now is 0.3. That would be sufficient according to Europam for the environmentally sensitive individuals, right? Now there's another point to this. We have shielded now the wiring inside the walls, but what do we still have? We have power cords to reading lights on any other appliances or alarm clocks or chargers or whatever you have. And almost all power cords we have in the United States are 2-pronged. That means they don't have a ground and they don't have a shield. So with other words, I shielded my walls, but I'm still going to get the electric fields from the plugged-in devices. So what can I do about that? 2 things. Number one, I could get the cheap version, which is a cutoff switch, which I plug in here, and it turns the circuit or the electricity off right here. So this will be de-energized. There will be no voltage present in here. If I would go to the light and turn the light off right here on its light switch, this would be still energized and the field would still be created, right? So what's the other option? The other option is getting some shielded power cords. You would have to get an electrician to install it onto your light fixtures. So anything around your bed, which you have shielded your bedside, you want to make sure that all the power cords which are going in there are either turned off at night or that you have a shielded system. So let's look at another scenario. So this is a new construction. And in the middle of the new construction, the client realizes that since they are building, it's just a good time to actually reduce the electromagnetic field exposure. So we were called in to deal with the children's bedrooms and the master bedroom, make sure that they have low EMF. Well, what turns out is The wiring is already installed. You see this white stuff? That's the Romex cable, and it's all over the place. So if the client installed, that was our first recommendation, install metal cladded armored cable, then that would shield it off and they wouldn't have to do anything else. However, the cost of replacing all the wiring and reinstalling all the wiring was substantial. So therefore, we chose a different scenarios, that we took a copper wire mesh, which is electrically conductive, and we put it up on the walls wherever we have electrical wiring. So here we got light fixtures and circuits running here. We got circuits running on the bottom. There's nothing going up and down. And now all of that gets shielded and then grounded out. And now drywall is being put back on and the electric fields are eliminated. Here we have an extra issue, that is, it's on the second floor. And there are light fixtures and wires in the flooring. So we put the copper wire mesh also on the floor. Let's do that step by step. So this client has an existing building and it's a master bedroom and they want to have it shielded against the electric fields, against radio frequencies, against dirty electricity. There was a magnetic field issue as well, but the electricians worked on it for a couple of days and found all the wiring errors and corrected them. So now we're going to install shielding in this master bedroom. This is how the master bedroom looks like in the beginning, before we start. When we use shielding paint, we always have to put a ground strap onto it, which will be visible afterwards, especially on flat wall surfaces. So our goal was to put it behind the baseboard so that it will not be visible. So we removed the baseboard, and since the baseboard, the drywall behind it isn't being primed, we use some primer coat so that we have a good surface to attach our grounding straps to. Here's the grounding straps, and these grounding straps go around all the walls, which are being painted with a shielding paint. And they go to a ground. We will ground it eventually. So now we have applied 2 coats of a shielding paint onto the wall surfaces. And now we need to put the shielding mesh onto the floor. Why do I use a copper wire mesh? Rather, why do I not paint the floor surfaces? For a very simple reason. If you look at it here, we got seams here in the wood, and the building is going to move and it's going to shake, and paint may crack or deteriorate, while a copper wire mesh is fairly flexible and it's going to endure movements and not be destroyed by it or torn. So that's why we use a wire mesh. So now we need to connect all of that to ground. So we have the straps here, which are coming from the painted surfaces on the walls. And then we have the copper wire mesh that all goes together on a grounding plate. And from a grounding plate, we have the grounding wire, and that grounding wire now goes to the electrical ground in the main system, electrical system. Or some people put a separate earth ground in there, basically just a stake, a copper stake in the ground, and then connect it to earth. All right. Now, before we put the finish coat on there, we want to verify that the results are sufficient. And so, we actually, you can see here, use a pole, which is non-conductive, so that we can actually measure the field coming out of the wall. So here are the results. So prior, we had like 17 to about 40 volts per meter on the different walls. And afterwards, we have levels between 0 and 0.2 on all the walls. We compare that to European guidelines. Daytime exposure was 10 volts, nighttime exposure 1 volt, and sensitive population 0.3 volts. So goal accomplished, I would say. Fairly straightforward scenario. And now the paint goes back on after we've verified and tested, because we can't go back here once it's painted. We won't be able to make a connection again, right? And the hardwood floors come in and the building is ready to be occupied. Okay. All right, so we talked about alternating current magnetic fields, alternating current electric fields, and now we're going wireless, all right? So the amount of devices which are coming online, which are wireless, are increasing exponentially. Every day, every minute, every hour. So we'll see a large number of radio frequency devices in our environment. It's increasing. So it ranges from broadcast towers to cell sites to baby monitors to Wi-Fi cordless phones, washing machines, PlayStations, Fitbits. We've even seen RF devices in diapers nowadays so that mom gets a signal on her smartphone that the diapers are wet, right? Okay. So a plethora of different devices which we can have emitting radio frequencies. We look at the outside antennas. Most of them are now camouflaged, so as trees. Sometimes you still see the poles. Sometimes there are pins hanging down from wires. And this is what we see more and more, that cell site antennas are attached to street light posts. And the design gets more sophisticated nowadays that you won't be able to actually realize anymore that there's an antenna on it. And that's what's moving into our residential areas with the 5G and the 4G advanced because we're using so much bandwidth, right? This is a church steeple which has been built, and you can see that's more of a large transmission station. This is a picture on a roof on a commercial building. They actually have a skirt around it so that you don't see the antennas, and that's a back view from the roof. And they even go to the extent of creating saguaro cactuses to camouflage devices. And I don't know if you recognize this here, the antennas on the chimney in the residential building. So they can be anywhere and everywhere. How do we identify that they're RF? We really need some equipment. So again, I make that point that we should have some equipment, some low-cost equipment just to check and make sure where we go that we identify where the sources are. Now, let's talk a little bit about the meters. I basically differentiate them into consumer-type meters, professional meters, and spectrum analyzers. Consumer-type meters are wonderful. They're inexpensive. They are very good scanning tools. The only limitations is they're not very accurate. So don't rely on the accuracy on it, but it needs, look at the trends of it. Look at what's your background, and when you go towards the source, what's the increase? Is it 10-fold, 100-fold, 1,000-fold, 10,000-fold, and so on. So very good screening tools. Professional, so the prices range between, let's say, $200 and $400 for these devices. Professional meters, you're in the $10,000 range. They're calibrated. They're expensive. They have different detectors, RMS and peak detectors, which is a whole nother story about the FCC compliance measurements because they're using an RMS detector, which always gives way lower levels than a peak detector. And spectrum analyzer is the tool for analyzing radio frequencies. So if you have the budget, you're talking about $10,000s of dollars, but that gives you the most information. The reason, again, why I'm telling you to have a meter in your pocket, this is a brand new commercial building, and a medical office moves in here. Of all things, it's a fertility clinic. And what do we have behind these soffits here in this new building? We can only see it because this worker is taking a panel off. They are cell sites. They're cell sites built into the exterior building envelope of this building. You wouldn't know it, you wouldn't smell it, you wouldn't hear it. You would only assess it with a measurement tool. This is a picture of a high-end boutique hotel guest room in Hollywood where you spend at least $350. But as a bonus, you can get a cell antenna in your guest room because there is a fake ventilation closet, air conditioning closet. You can see here the vents. But what's really in there is a cell antenna. which moves obviously to the outside, to the exterior, but it also gives off RF levels to the back and to the side. So it puts it also into this room. The other guest room we actually have two of those closets. There's a whole bank of cellular antennas in it. You wouldn't realize it unless your meter would start going off the scale. Okay. And another difficulty we actually have with measuring radio frequencies is the fluctuations, because the level of RF varies with the traffic load. That means how many people are logged on, how many using the service. So with other words, you can go out to a site, measure in the morning, measure in the afternoon, and get two different results. That has to do with the fluctuation, right? To really identify what kind of RF fields are present, the spectrum analyzer is the most helpful tool. How does it work? Well, you have a scale down here, which shows you the frequency in megahertz, so 500,000, 1,500, and so on. And then we have a scale of amplitude. That means the power, how much is there. Now, this is a logarithmic scale. So, and then we know what kind of frequencies are associated with what kind of a service. So we know that FM radio this is FM radio, all the FM radio stations. These are TV stations. These are cellular bands. This is from a transponder from an airplane which flew overhead while we were doing our measurements. And here are cellular band, and here is the Wi-Fi. So a spectrum analyzer allows us to really identify what sources are there and to which magnitude are they there, right? Are there other ways? Yeah, there are some websites where you can actually punch in your home address, and it will kind of like tell you what kind of towers are in your vicinity. I have used it, and I must say, unfortunately, they are not very accurate. They're not very much updated. We do not have one singular database in the United States where all antennas are listed and where we can look them up. That is in contrary to the Europeans. In Europe, you can go to a government website, you can punch in your address, and you can see the type of antenna. All of them need to be registered on a map and registered with an agency. Different in the United States. What do we do? How do we deal with radio frequency fields? Okay, well, a couple of solutions, all right? So first of all, we have to differentiate between interior sources and exterior sources. So over exterior sources, we have very little control. The broadcast tower, the cell sites, and so on. But the interior sources, that's where we have the control. As I measured in my introduction, the Wi-Fi, the cordless phone were the predominant RF sources in this particular residence. And the concern was about the cell site. So once we take measurements, we can then associate where the predominant fields are coming from. So let's deal with the inside sources. So what's the first way? Elimination. Can we let go of it, right? If not, can we replace it with a less emission device? Can we shield it? Or can we let go of it? And we shouldn't forget the most significant indoor RF source is our cell phone. What are some other ways of controlling it? Well, let's have a look. So shielding materials are paints, films, meshes, copper wire meshes, and so on. They can apply to wall surfaces, to flooring, to glass panes, and so on. And we can create shielding. Now, when we talk about shielding, there's something which is called the shielding efficiency. Every product data sheet is going to tell you how much it's going to reduce the field. And we have a couple of different terms. Number one is the reduction in percentage. So 90%, 99%. We have the reduction factor, let's say, 10-fold or 100-fold reduction. But what you will see in the documents is what is referred to as dB. And so that's the terminology which is used in the industry. So a minus 10B reduction means a 90% reduction. A 20 dB rating on the material means a 99% reduction. What does it mean? Let's say I measure 100,000 before I start shielding. I choose a material and I get a 30 dB reduction, then I have 130 on my indoor environment. Now there's one flaw in this whole system here, and that is when they actually test the materials, they take one piece, and they have an antenna going here, sending it out a signal, have an antenna here, absorbing the signal. But you're basically looking at a small surface area. And if you install that material in the building, you're not going to get the same results. Why? Because you got openings, you got windows, you got doors, you got chimneys, you got vent pipes, you get cracks and crevices and so on. So whatever it lists on your material data sheet is not necessarily what you're going to get when you install it. So that's where the measurements before and after come in handy. All right, I mentioned already the cell phone. So, make sure you shield your cell phone. There are different type of coverings out there, pouches. This is my favorite one. The beautiful fabric, and it has shielding material on the inside. And so that I think everyone should have who's concerned about EMF or RF exposure. There are also a lot of self-made tools. So for example, what I did here right now is I took a window screen out, which is a fly screen, took that mesh out and put a Coopertech wire mesh on in here. And now I got a fly screen made out of an RF shielding material. Well, maybe it only covers half the window because only the movable part has a screen, right? Well, you could make this larger than your window is, overlapping the entire size of your window, and attach it to the outside of your building, and then you have a shielding, very highly effective shielding material to deal with your windows. Windows are the largest hole in a building envelope when you talk about radio frequencies, unless you've got double pane glass with an E rating. That means it's an energy efficient glass. This is what a lot of people utilize. That's called a bed canopy. And this is a radio frequency shielding fabric, and it's now put over the entire bed. A lot of people like it because I don't need to shield the walls and windows and everything else, but I'm sleeping under a canopy. So what we did is here's a little bit of a measurement protocol to see how it works. So here's a spectrum analyzer. We're measuring in the center of the bed. The lady actually had also a curtain. Here's a window, a curtain with the same material here. And so we're just measuring and comparing. So what do we see? When we have the bat canopy off and the window curtains off, we measure about 1,500 microwatts per meter square. Then we put the window curtain on, and it doesn't really do anything just by itself. Now, once we put the bat canopy on it, then the level really goes down by more than an order of magnitude. We have an efficiency of 96%. That is a good reduction, or expressed in dB, 14 dB reduction. Now, what I did is I removed the curtain a bit to see what the difference is. Not significant, so the curtain is not really doing a lot. It's the bat canopy. However, what I realized is, what I did is I actually, you see that it's going to be difficult to put that canopy all the way to the bottom. It only works perfectly when it's all the way on the bottom, that fabric. So this one was a little bit left open in the back here because it was difficult to put it down behind the headboard. So, and with it partially off, I get 800 or 900 microwatts in the center of the bed. And when I moved my instruments to the head area of the bed, it went up to 1,200. What's the moral of this? The bed canopies only work if you really, really fully enclose it and you don't have it lifted up somewhere. Yeah, I personally have a little difficulties with the bed canopies due to being claustrophobic in there and lack of good air ventilation. Okay, so let's look at a couple of shielding systems. So we can apply shielding materials to a building from the exterior, by using some copper wire mesh or by using some shielding paints. We can have interior application where we either use the copper wire mesh or we use the paint, as we already saw that in a couple of applications in real life mitigation situations. For example, they can be put on roof assemblies. We have cell towers here, and the residents wanted to prevent them from the exposure from the cell towers. And so since a new roof was coming on anyway, they put a membrane underneath it. How does that work? Just to give you an example, this is a commercial building. This caboose houses a cell site. So there's a tower in here with a lot of antennas on here. So this is just a fake house. The building owner had to replace his roof, and he thought it would be a good idea just to put a shielding membrane underneath it, so that his tenants are going to be protected from the RF exposure. So this is how the copper wire mesh looks like. There are connections, and these connections are essential because the weakest point in an RF shielding is the connection between two different layers. And you can see this has a felt seam system in itself, and then it's stapled very tight together. So here you can see the different lines going out. Now, when we shield a building, what we also need to think about is penetrations. And the penetrations need to be incorporated into the shielding envelope. So that is very important to do so. And you can see the whole roof. They actually lifted this off so that we could put the material underneath it, and then the service provider put it back down on the bottom. We need to ground the system, as mentioned before. And then the regular roofing membrane goes back on top, and here's the completed roof assembly. Yeah. So coming back to this particular building, we've seen this before, right? So because one of the doctors had a RF meter in its pocket, and it went off the scale once he went into his beautiful new office, it was still to be built out, he realized that there was something going on. So we come in, we measured it, we've identified it, and now what do? So the antennas are sitting in this bump out here, which is basically the window sill, and half the antenna is on this floor and half the antenna is on the floor below. So this is where, and the doctor is going to sit right here with his back about a foot or two from the antennas. So what can we do? Well, we applied shielding materials to the walls, to the floors, and especially to the bump out area, where we actually put 2 layers of shielding material on there to create a reduction. So this is how this is being installed. You basically, again, want to make sure that the seams are very tight. It's done with copper staples here to connect the 2 different layers of it. Okay, so, and again, the grounding, very important, needs to be attached to it. And now the construction workers are just putting drywall back on top of it, and nobody knew that there was anything shielding material-wise installed into that particular building. That's my last application here. So this is a new construction, and the owner says, I want an EMF sanctuary. I don't want to address the rest of my house, but I want to address the rest area, the master bedroom. And I want to have it shielded against radio frequencies, against electric fields, and against dirty electricity. The magnetic fields we already addressed in the construction process, so that there will be no large magnetic fields in the master bedroom. So this wire mesh is being attached to surfaces and floors, and sometimes there are a lot of details which need to be worked out, data cables and so on. So you need to actually create openings so that all of this can come out. You can put shielding materials on top of roofs. Very often antennas are high up, so the main surface area, how it enters the building, is through the roof. If you have a tile roof, you can take the tiles off on top, store them over here on the bottom side, put this shielding material down, attach another layer of it, and then put the tiles back on. And so you continue while by removing moving tiles off and moving tiles back into the area. Now, this is a picture of a research laboratory. They wanted a room with absolute zero for a university. And so 2 layers are actually installed so that you get the double or a better shielding effect than just 1 layer. But what I want to put your eyes onto is the incoming wires. So all the data cables and electrical wiring all is shielded as well. So to prevent any dirty electricity coming in here or other waves riding on the wires coming into the place, they actually had that shielded as well. And what we have at the end where we have electrical supplies, we actually have a filter so that any type of dirty electricity is being filtered out inside this particular room. What are some of the guidelines? Where would we like to be in terms of RF exposure? Again, this is the European guidelines, daytime, nighttime sensitive population. And these they actually differentiate by the different type. If you're talking about digital TV or if we're talking about cellular, and so on. But basically, we usually use the criteria of about less than 1,000 or less than 100, depending on what's economically achievable. And if we have very sensitive individuals, get it down to a level of 1 is not an easy task in today's environment. Okay. What are some other standards? The building biology says that, well, between 0.1 and 10 is kind of okay. And they don't want to see anything above 1,000. That's the same as the bioinitiatives report says. Okay, lastly, we come to the topic of dirty electricity. That is quite a complex topic, and there are really no simple ways to identify or eliminate dirty electricity. Well, what is it in the first place? Well, it's basically other frequencies, higher frequencies, riding on top of the 60 hertz power frequency. We can measure it with oscilloscopes, and what will happen is, with these higher waveforms, is that the sinusoidal wave form gets distorted, and that other signals riding on top of it. Dirty electricity is currently a big topic in the arena of EMF. It's not easy to identify and rectify. All right, let's look at it a little bit. So here I have an instrument where I actually do a spectrum analysis. I have 1 kilohertz, 2 kilohertz, 10 kilohertz. Here's my 60 hertz signal. And you can see there are a couple of peaks. We call them harmonics, which is a multitude of the fundamental frequency. And here is a little bit of crizzle, but not much. But if we look at another location, we can see that there are a lot of peaks in 1 kilohertz, 2 kilohertz, up to the 3 kilohertz version. So there is a source, a dirty electricity source present. Same here. Another scenario on this particular building, we see a little peak of 10 kilohertz. And then in this building, we see peaks of a lower frequency in here. Again, 10 hertz peak. Here is a 25 kilohertz peak. So the question is, where are they coming from? Well, anytime you convert the voltage. In the old days, we used to have transformers, one transformer for 120, and then we convert that down to, let's say, to 12 volts with magnets and wires. That has gone away. Those were the big bricks we used to carry around with our laptop computer. And nowadays, that's done electronically. And when they do that electronically, they distort the signal, and then we get many of the other peaks coming up. What are some of the culprits who are doing that? Any type of a power supply, which is a low voltage power supply for computers, lights, and so on, smart meters, and also the utility electrical current, which already comes into your system, may already have dirty power on it. So the best way is to identify the sources which are creating the dirty electricity and to take them out. For example, dimmer switches are also a source. But we have so many devices in our homes that it is almost impossible to get rid of all of the dirty electricity sources. There's an excellent paper, by the way, if you want to look that up. It was in the Journal of Exposure Science and Environmental Epidemiology, titled Dirty Electricity: What, Where, and Should We Care? And highly recommend that you have a look at it. So what does one do for the treat? What's the treatment? Well, there are a lot of plug-in filters which are being sold all over the place. So you actually plug it into your electrical outlet, and then supposedly it dissipates. A lot of people feel better afterwards. A lot of scientists say, well, we don't really know if this is the right way to go. One can show that these frequencies move somewhere else. However, we need to understand that this is not the best solution, because they actually use electrical power and they also heat up. And if you have wiring errors inside the house, then they can create large magnetic fields and they can create fire hazards. So you want to make sure that you don't have any wiring errors before you plug these things in. Okay. What is a more effective way is to actually have a whole house filtration system. So there are boxes which one can purchase, which are then installed as close as possible to the electrical panel. And there are different manufacturers here. Again, there are different opinions out there. There is no standardized testing procedure, no standardized evaluation procedure at this point of time for dirty electricity. So we're flying a little bit on the seat of our pants, if I can say it that way. Eventually, there's a company who's trying to develop a device which we can just plug in, and we can actually visibly see the different harmonics or the different distortions on the system, and then actually monitor and see, as we are removing items, that we're actually cleaning up the environment. This concludes my lecture, except for this last slide here. I just wanted to point out one more time. There are large filters out there. They call them whole house filters, or they are installed on an entire circuit, and they will filter out the dirty electricity from that particular circuit. But however, they are in the range of about $1,000 to $2,000 a pop. So not something which is inexpensive. And you can see, for example, that it says here that it has a dB rating of 100. So it reduces by 99.99999% of the field which was there, and it filters out from 14 kilohertz to 10 gigahertz. So those are the specifications you may want to look at if you're looking at a filter. All right, so that concludes my presentation here on how to identify and how to mitigate the indoor environment. If you have any further questions, feel free to bring them up now, or give us a call, or send us an email later on. Thank you.